Welcome back to my channel LinkedIn Farmer. Today's video is based on motion, chapter 7, class 9. Before starting this video, please like and subscribe to my channel. Let's start it. Introduction. Motion is a fundamental concept in the realm of physics in our everyday lives. It refers to the change in an object's position with respect to time. Whether it's the graceful flight of a bird, the swift rush of a sprinter, or the gentle sway of tree branches in the wind, motion surrounds us and plays a vital role in understanding the dynamics of the world we inhabit. In this brief exploration, we'll delve into the essential principles of motion and its significance in our universe. Describing motion. Motion is the act of an object changing its position in space over time. A simple example is a car moving along a road. As the car travels from one point to another, it experiences motion, demonstrating how objects can shift from one location to another, illustrating the fundamental concept of motion in our physical world. Motion along a straight line. Motion along a straight line, often referred to as one-dimensional motion, occurs when an object moves only in a single direction, either forwards or backwards, along a linear path. This type of motion is relatively straightforward to describe and analyze. Here's an explanation with an example. Explanation. In one-dimensional motion, an object's position is defined by a single coordinate, typically referred to as x, which represents its location along the straight line. The change in position over time is what we call displacement, denoted as delta x. If an object's displacement is positive, it means it moved in one direction, example, to the right, and if it's negative, it moved in the opposite direction, example, to the left. Example, imagine a car traveling along a long, straight highway. The car starts at mile marker 0 and proceeds to drive in the forward direction. As it moves, its position changes along the highway, and we can describe its motion along the straight line. Let's say after 2 hours of driving, the car has reached mile marker 120. In this example, the initial position of the car was at mile marker 0. The final position of the car is at mile marker 120. The displacement of the car is delta x equals 120 miles, positive because it moved forward. The time taken for this motion is 2 hours. We can calculate the car's average speed by dividing the displacement by the time taken. Average speed equals delta x by delta t. Average speed equals 120 miles per 2 hours. Average speed equals 60 miles per hour. So, in this scenario of motion along the straight line, we can quantify the car's position, displacement, and speed, providing a clear understanding of its one-dimensional motion. Uniform motion and non-uniform motion. Uniform motion. Uniform motion refers to an object's movement along a straight line where it covers equal distances in equal intervals of time. In other words, the object travels at a constant speed without changing its direction. Here's an explanation with an example. Example of uniform motion. Imagine a car driving on a straight highway at a constant speed of 60 miles per hour. In this case, the car covers the same distance every hour, maintaining a steady pace. If it travels for 1 hour, it will have covered 60 miles. After 2 hours, it will have covered 120 miles. After 3 hours, it will have covered 180 miles. This demonstrates uniform motion because the car's speed remains constant, and it covers equal distances in equal intervals of time. Non-uniform motion. Non-uniform motion, on the other hand, occurs when an object's speed or direction changes as it moves along a straight line. In this type of motion, the object covers unequal distances in equal intervals of time or equal distances in unequal intervals of time. Here's an explanation with an example. Example of non-uniform motion. Consider a cyclist pedaling along a straight road. Initially, the cyclist accelerates slowly, then reaches a constant speed, and eventually decelerates to a stop. In this case, during the initial phase, the cyclist covers a short distance in a certain amount of time, so the speed is low. Once the cyclist reaches a constant speed, they cover longer distances in the same amount of time, indicating a constant speed. Finally, When the cyclist starts applying the brakes to stop, they cover a shorter and shorter distance in each successive moment until they come to a halt. This represents non-uniform motion because the cyclist's speed varies throughout the journey, covering unequal distances in equal time intervals. In summary, uniform motion involves constant speed and equal distances covered in equal time intervals, while non-uniform motion involves changing speed or unequal distances covered in equal time intervals. Measuring the rate of motion. Measuring the rate of motion involves quantifying how fast an object is moving, typically in terms of distance covered per unit of time. The most common unit of measurement for motion rate is speed, which can be expressed in various units such as meters per second, miles per hour or kilometers per hour. Here's an explanation with an example. Example of measuring the rate of motion. Let's say you have a friend who is running a race, and you want to measure their rate of motion or speed. You decide to use meters per second as your unit of measurement. 1. Position measurements. You record your friend's position at different time intervals using a stopwatch and a measuring tape. Here's the data you collect. 2. Calculating speed. To calculate your friend's speed, you can use the formula. Speed, meter per second, equals distance, m, divided by time, s. 3. Average speed. In this example, your friend's speed remains constant at 5 meters per second throughout the race. This is called the average speed because it's the same over equal intervals of time. So, in this case, your friend's rate of motion or speed is 5 meters per second, indicating that they covered 5 meters of distance every second during the race. Measuring the rate of motion is crucial in various fields, including physics, sports, and transportation, as it helps us understand how quickly objects or individuals are moving relative to time, making it a fundamental concept in the study of motion. Where displacement is the change in position, which considers both distance and direction. Example, suppose you drive a car from your home to a grocery store, which is 10 kilometers to the north. If it takes you 20 minutes to make this trip, you can calculate your velocity as follows. Velocity equals displacement per time equals 10 kilometers north per 0.333 hours. Approximately equals 30 kilometers per hour north. So, your velocity in this example is approximately 30 kilometers per hour to the north. In both examples, measuring the rate of motion is crucial for understanding how quickly an object is moving relative to time, and whether direction is considered or not depends on whether you are dealing with speed or velocity. Example, an object travels 16 meters in 4s and then another 16 meters in 2s. What is the average speed of the object? Solution. Total distance traveled by the object equals 16 meters plus 16 meters equals 32 meters. Total time taken equals 4 second plus 2 second equals 6 second. Average speed equals total distance traveled per total time taken equals 32 meters per 6 second equals 5.33 meters second inverse. Therefore, the average speed of the object is 5.33 meters second inverse. Speed with direction. When we discuss speed with direction, we are referring to velocity. Velocity is a vector quantity that not only considers the speed, magnitude, of an object's motion but also its direction. Unlike speed, which is a scalar quantity, velocity specifies both how fast an object is moving and the direction in which it is moving. Speed, magnitude, speed refers to how fast an object is moving without considering its direction. It is a scalar quantity and is usually measured in units such as meters per second, kilometers per hour, or miles per hour. Direction, vector, direction specifies the path or orientation along which an object is moving. It is crucial to fully describe the object's motion. Direction is typically given using compass directions, examples, north, south, east, west, or angles, examples, 45 degrees clockwise from east. Velocity, vector. Velocity is a vector quantity that combines speed and direction. It represents how fast an object is moving in a particular direction. In mathematical terms, velocity, v, is defined as velocity, v, equals speed, s, times direction, theta. Where Velocity, v, is a vector with both magnitude and direction. Speed, s, is the magnitude of velocity, how fast the object is moving. Direction, theta, specifies the orientation or angle of motion. Example, let's consider a car for illustration. If the car is moving at 60 km per hour speed and traveling north direction, then its velocity is 60 km per hour north. Here's a breakdown. Speed, magnitude, 60 km per hour. Direction, north. So, the car's velocity is 60 km per hour north, which provides a complete description of its motion. In summary, speed with direction, or velocity, takes into account both how fast an object is moving, speed, and the specific path or orientation it follows, direction. This combination results in a vector quantity, which provides a more comprehensive understanding of the object's motion than just speed alone. In case the velocity of the object is changing at a uniform rate, then average velocity is given by the arithmetic mean of initial velocity and final velocity for a given period of time. That is, average velocity equals initial velocity plus final velocity divided by 2. Mathematically, VAV equals U plus V2, where VAV is the average velocity, U is the initial velocity and V is the final velocity of the object. Speed and velocity have the same units, that is, m second inverse or meter per second. Rate of change of velocity. 1. Velocity. Velocity is a vector quantity that describes an object's speed and direction of motion. It specifies both how fast an object is moving and the path it is following. 2. Change in velocity, delta v, the rate of change of velocity, often denoted as delta v, represents how much an object's velocity changes during a certain time interval. This change can occur in terms of speed, direction, or both. 3. Time interval, delta t, the rate of change of velocity is calculated over a specific time interval, denoted as delta t. This interval represents the duration during which the velocity change is measured. 4. Formula. The rate of change of velocity can be mathematically expressed as rate of change of velocity equals delta v divided by delta t, where dt by dv equals represents the rate of change of velocity. Delta v is the change in velocity during the time interval delta t. Delta t is the time interval during which the change in velocity occurs. 5. Interpretation. The rate of change of velocity tells us how quickly an object's velocity is changing. If the rate is positive, it means the velocity is increasing, acceleration, while if it's negative, the velocity is decreasing, deceleration. If the rate is 0, the velocity remains constant. 6. Example. Imagine a car accelerating from a standstill. At time t1, the car has a velocity of 0 meters per second, and at time t2, it has a velocity of 20 meters per second. The change in velocity, delta v, during this time interval is 20 meters per second, positive because it's accelerating, and the time interval, delta t, is, for instance, 5 seconds. Therefore, the rate of change of velocity is dv by dt equals delta v by delta t equals 20 meters per second, 5 equals 4 meters per second square. So, the car is experiencing a rate of change of velocity of 4 meters per second squared, which indicates it's accelerating at this rate. Graphical representation of motion. A graphical representation of motion is a visual way to depict the movement of an object over time. It helps us understand and analyze an object's position, speed, and acceleration as they change with respect to time. Here's an explanation of key components in a graphical representation of motion. 1. Time axis, x-axis, the horizontal axis on the graph typically represents time. Time is measured in consistent intervals, such as seconds, minutes, or hours, and is usually plotted from left to right. 2. Position or displacement axis, y-axis, the vertical axis on the graph represents the object's position or displacement. Position is measured in units like meters, kilometers, or miles and is plotted vertically. 3. Position time graph, displacement time graph. This type of graph shows how an object's position changes over time. The slope of the graph at any point represents the object's instantaneous velocity. A straight line indicates constant velocity, while a curve indicates changing velocity, acceleration or deceleration. 4. Velocity time graph. This graph displays how an object's velocity changes over time. The slope of the graph at any point represents the object's instantaneous acceleration. A horizontal line indicates constant velocity, zero acceleration, while a non-horizontal line represents acceleration or deceleration. 5. Acceleration time graph. While less common, this graph illustrates how an object's acceleration changes over time. The slope of this graph at any point represents the rate of change of acceleration. 6. Key features. Various features can appear on these graphs, including straight lines, curves, peaks, valleys, or points of intersection. These features provide insights into the object's motion characteristics, such as constant velocity, changing velocity, rest, or acceleration. 7. Example. Consider a car accelerating from rest. On a position time graph, initially, there is a horizontal line, the car is not moving, followed by a diagonal line sloping upwards, the car is accelerating. On a velocity time graph, there will be a diagonal line sloping upwards, positive acceleration. And on an acceleration time graph, there will be a horizontal line, constant acceleration. In summary, a graphical representation of motion is a powerful tool for analyzing and visualizing how an object's position, velocity, and acceleration change over time. These graphs provide valuable insights into the dynamics of motion, making them essential in the field of physics and engineering. Distance time graph. A distance time graph, also known as a displacement time graph, is a graphical representation that shows how the position or displacement of an object changes over a specified period of time. It provides a visual way to understand and analyze an object's motion, particularly in terms of distance or displacement. Here's an explanation of key components and concepts related to distance time graphs. 1. Time axis, x-axis. The horizontal axis of the graph represents time, typically measured in consistent intervals, examples, seconds, minutes, or hours. Time is plotted from left to right. 2. Distance or displacement axis, y-axis. The vertical axis represents the object's distance or displacement from a reference point. Distance or displacement is measured in units such as meters, kilometers, miles, or any other relevant unit. 3. Straight line. A straight line on a distance time graph indicates constant speed or velocity. The slope of the line represents the object's speed, with a steeper slope indicating a faster speed and a shallower slope indicating a slower speed. 4. Curve. A curved line on the graph signifies a change in the object's speed or velocity. The curvature can be upward, indicating acceleration, downward, indicating deceleration, or a combination of both. 5. Flat line. A horizontal line at a certain distance level indicates that the object is at rest and not changing its position. In this case, the object's speed is 0. 6. Gradient, slope. The gradient or slope of a line at any point on the graph represents the object's instantaneous speed or velocity at that moment. The steeper the slope, the greater the speed. 7. Area under the graph. The area between the graph and the time axis represents the total distance traveled by the object during the specified time interval. Calculating this area can provide information about the total displacement or distance covered. 8. Example. Suppose you have a distance time graph of a car's motion. A straight diagonal line rising from left to right indicates that the car is moving at a constant speed. A curve that slopes upward suggests that the car is accelerating, while a curve sloping downward indicates deceleration. A horizontal line segment means the car is stationary. In summary, a distance time graph is a valuable tool for visualizing and understanding how an object's position or displacement changes over time. It provides insights into the object's speed, direction, and any changes in its motion, making it a fundamental tool in physics and kinematics. Velocity time graphs. A velocity-time graph, also known as a speed-time graph, is a graphical representation that shows how an object's velocity, or speed, changes over a specified period of time. It provides a visual way to understand and analyze the object's motion, focusing on how its speed varies with time. Here's an explanation of the key components and concepts related to velocity-time graphs. 1. Time axis, x-axis. The horizontal axis of the graph represents time, typically measured in consistent intervals, examples, seconds, minutes, or hours. Time is plotted from left to right. 2. Velocity or speed axis, y-axis. The vertical axis represents the object's velocity or speed. Velocity is a vector quantity that includes both the magnitude, speed, and direction of motion. Speed is a scalar quantity representing the magnitude of velocity. Velocity or speed is measured in units like meters per second, kilometers per hour, or miles per hour. 3. Straight line. A straight line on a velocity-time graph indicates constant velocity or speed. The slope of the line represents the object's acceleration, with a positive slope indicating acceleration, a negative slope indicating deceleration, and a zero slope indicating constant velocity, zero acceleration. 4. Curve. A curved line on the graph signifies a change in the object's acceleration. The curvature can be upward, indicating positive acceleration, downward, indicating negative acceleration or deceleration, or a combination of both. 5. Flat line. A horizontal line at a certain velocity or speed level indicates that the object is moving at a constant speed with no acceleration or deceleration. 6. Gradient, slope. The gradient or slope of a line at any point on the graph represents the object's acceleration at that moment. The steeper the slope, whether positive or negative, the greater the acceleration. 7. Area under the graph. The area between the graph and the time axis represents the total displacement or distance traveled by the object during the specified time interval. Calculating this area can provide information about the total displacement or distance covered. 8. Example. If you have a velocity-time graph of a car's motion, a straight horizontal line indicates that the car is moving at a constant speed, constant velocity, while a curved line sloping upward indicates acceleration. A curve sloping downward represents deceleration or negative acceleration. In summary, a velocity-time graph is a valuable tool for visualizing and understanding how an object's velocity or speed changes over time. It provides insights into the object's acceleration, direction of motion, and any changes in its speed, making it essential in the field of physics and kinematics. Equation of motion. Equations of motion are a set of mathematical equations used to describe the motion of objects in physics. These equations relate an object's position, velocity, acceleration, time, and other relevant parameters as it moves in a straight line under the influence of constant or changing forces. They are fundamental tools for analyzing and predicting the behavior of objects in motion. There are three primary equations of motion that are commonly used, and they apply to objects with constant acceleration, acceleration that doesn't change over time. Here they are. 1. First equation of motion, or displacement equation. Delta x equals v0t plus 1/2 at square. Where delta x is the displacement, change in position, of the object. v0 is the initial velocity of the object. T is the time elapsed. A is the constant acceleration of the object. This equation relates the displacement, initial velocity, time, and acceleration of an object undergoing constant acceleration. 2. Second equation of motion, or velocity equation. V equals v0 plus at, where v is the final velocity of the object. v0 is the initial velocity of the object. T is the time elapsed. A is the constant acceleration of the object. This equation relates the final velocity, initial velocity, time, and acceleration of an object. 3. Third equation of motion, or time equation. Delta x equals 1/2 v0 plus vt, where delta x is the displacement, change in position, of the object. v0 is the initial velocity of the object. V is the final velocity of the object. T is the time elapsed. This equation relates the displacement, initial velocity, final velocity, and time taken by the object. These equations are incredibly useful for solving a wide range of problems related to the motion of objects, whether they are free-falling, moving along an inclined plane, or undergoing any form of linear motion. They allow scientists and engineers to predict an object's position, velocity, and acceleration at any point in time, given the appropriate data and conditions. Uniform circular motion is a specific type of motion in which an object moves along the circumference of a circle at a constant speed while continuously changing direction. This means that the object covers equal distances around the circle in equal time intervals, creating a circular path. Several key characteristics define uniform circular motion. Constant speed. In uniform circular motion, the object travels at a constant speed throughout its motion. The magnitude of its velocity remains the same, but the direction of velocity changes continuously. Circular path. The object follows a circular trajectory or path, with a fixed radius. The radius is the distance from the center of the circle to the object. Centripetal acceleration. Despite the constant speed, the object experiences acceleration. This acceleration is directed toward the center of the circle and is called centripetal acceleration, AC. It is responsible for changing the direction of the object's velocity without altering its speed. The centripetal acceleration is given by the formula AC equals v square by r, where v is the magnitude of the object's velocity. R is the radius of the circular path. Centripetal force. To maintain uniform circular motion, an object must experience a force directed toward the center of the circle. This force is called the centripetal force. The centripetal force provides the necessary inward acceleration to keep the object in its circular path. Angular velocity. Uniform circular motion can also be described using angular quantities. Angular velocity, omega, represents how quickly the object traverses an angular displacement, angle, in a given time. The relationship between linear velocity, v, angular velocity, omega, and radius, r, is v equals omega r. Examples of uniform circular motion include a car making a turn on a circular track at a constant speed, a planet orbiting the sun, or a ball spinning around the inside of a centrifuge. In all these cases, the objects are continuously changing direction while maintaining a constant speed, resulting in uniform circular motion. Uniform circular motion. Uniform circular motion is a specific type of motion in which an object moves in a circular path at a constant speed. In this type of motion, the object's speed remains unchanged, but its direction continuously changes as it travels around the circle. Here are the key characteristics and concepts associated with uniform circular motion. Constant speed. In uniform circular motion, the object moves at a constant speed. This means that the magnitude of its velocity, speed, remains the same throughout the motion. However, because it is moving in a circle, the direction of its velocity is constantly changing. Continuous change in direction. The object in uniform circular motion continuously changes its direction as it goes around the circle. This change in direction implies that there is an acceleration acting on the object, even if its speed remains constant. Centripetal acceleration. The acceleration directed toward the center of the circle is called centripetal acceleration. This acceleration is responsible for keeping the object in its circular path. It is always perpendicular to the object's velocity in points toward the center of the circle. Centripetal force. According to Newton's second law of motion, F equals ma, if an object is undergoing centripetal acceleration, there must be a force acting on it. This force is called the centripetal force and is responsible for keeping the object moving in a circle. The centripetal force must always be directed toward the center of the circle. Examples of uniform circular motion. Planetary orbits. Planets in our solar system, like Earth, orbit the Sun in approximately circular paths. They maintain a constant speed as they move in their orbits. Car on a banked curve. When a car drives around a banked curve on a road at a constant speed, it undergoes uniform circular motion. The friction between the tires and the road provides the necessary centripetal force. Spinning objects. Objects like a spinning top or a rotating ceiling fan also exhibit uniform circular motion. Period and frequency. In uniform circular motion, the time it takes for the object to complete one full circle is called the period, t, measured in seconds. The reciprocal of the period, 1 by t, gives the frequency, f, measured in hertz, which represents how many complete circles the object makes in 1 second. Angular speed. Uniform circular motion can also be described in terms of angular speed, omega, measured in radians per second. Angular speed relates to the rate at which an object sweeps out angles as it moves around the circle. In summary, uniform circular motion involves an object moving in a circular path at a constant speed. This motion requires the presence of a centripetal force, which continuously changes the object's direction and keeps it in the circular path. Understanding uniform circular motion is essential in various fields, including physics, engineering, and astronomy. Thank you for watching.